Today's lesson is about conservation of mechanical energy. Lesson 4.2.3 Conservation of mechanical energy. By the end of the period, with at least 80% mastery, students will be able to state the law of conservation of energy, solve problems using the law of conservation of mechanical energy. Background information. Recall that energy is defined as the ability to do work. Work is done when energy is transferred from one system to another. For instance, when a force is applied to an object. Energy may be either potential or kinetic. Potential energy P is energy stored and ready for use. A car stopped at the top of a hill has potential energy. Potential energy is measured by the amount of work the object can perform. Kinetic energy, Ke, is the energy of motion. A car rolling downhill has kinetic energy. The law of conservation of energy states energy cannot be created or destroyed. It can be transformed from one form into another, but the total energy remains constant. Energy can be transformed into non-useful forms like heat or friction. Here are some examples of energy transformations and their uses. A television changes electrical energy into sound and light energy. A toaster changes electrical energy into thermal energy. A car changes chemical energy from fuel into thermal energy and mechanical energy. A flashlight changes chemical energy from batteries into light energy. When you speak into your telephone, sound energy from your voice is changed into electrical energy. The electrical energy is then converted back into sound energy on another phone, allowing someone to hear you. Campfires convert chemical energy stored in wood into thermal energy, which is useful for cooking food and staying warm. Nuclear energy generates a tremendous amount of thermal energy, which can be converted into electrical energy in a nuclear power plant. Sunlight shines on a person's face and changes to thermal energy. Solar-powered car. Most cars run by using a battery for electrical energy and gasoline for chemical energy. A solar-powered car can go using energy from the sun. Let's look at some examples of energy transformations between potential and kinetic energy. One of the most common energy transformations is the transformation between potential energy and kinetic energy. In waterfalls such as Niagara Falls, potential energy is transformed to kinetic energy. The water at the top of the falls has gravitational potential energy. As the water plunges, its velocity increases. Its potential energy becomes kinetic energy. The energy transformation in a pendulum. In a pendulum, a continuous transformation between kinetic and potential energy takes place. At the highest point in its swing, the pendulum has no movement. so it only has gravitational potential energy. As it swings downward, it speeds up. Its potential energy is transformed to kinetic energy. The pendulum is at its greatest speed at the bottom of its swing. There, all its energy is kinetic energy. As the pendulum swings to the other side, its height increases. The pendulum regains gravitational potential energy and loses kinetic energy. At the top of its swing, it comes to a stop again, and so the pattern of energy transformation continues. Here is the energy transformation in a pendulum. At the greatest height, potential energy is greatest and no kinetic energy. At the bottom part, we have the greatest kinetic energy but no potential energy. And on the other side, the greatest height, you have the greatest potential energy but no kinetic energy. So, in a conservation of mechanical energy, the kinetic energy plus the potential energy equals total energy, or 1/2 mv squared plus mgh equals E, where m is the mass, v is the velocity, g is the gravitational acceleration, which is 9.8 meters per second squared, and h is the height. As a coaster car loses height, it gains speed. Potential energy is transformed into kinetic energy. As a coaster car gains height, it loses speed. Ke is transformed into Pe. The sum of the Ke and Pe is constant. The same is true in this illustration. The total energy remains constant. Potential and kinetic are changing. Also here, the kinetic energy and potential energy are changing, but the total mechanical energy remains constant. Let us solve some problems now involving the conservation of mechanical energy. We learned that kinetic energy plus potential energy is total energy, and between any 2 points, say 1 and 2, kinetic energy at point 1 plus potential energy at point 1 equals kinetic energy at point 2 plus potential energy at point 2. Solve the following problems. A 5-kilogram ball hangs on a chain from a hook in the ceiling. The ball is pulled back along its arc to point A and released from rest at a height of 3 meters above the ground. The ball passes through its lowest point on the path, which is the point B closest to the ground, just above the ground, as you can see in this picture here. Letter A. Calculate the potential energy and kinetic energy at point A. So at point A, only potential energy is present. We use the formula potential energy at point A equals m times g times height. So substituting the values, we have 5 times 9.8 times 3 equals 147 joules. And the kinetic energy is 1/2 mv squared. And since V is 0, it starts from rest, then 1/2 times 5 times 0 squared equals 0 joules. Determine the total energy at point A. The total energy at point A is the sum of the potential energy at point A and kinetic energy at point A. So 147 plus 0 equals 147 joules. Letter C. Determine the total energy at point B. At point B, that is the lowest point, the height therefore is 0. So the total energy at point B equals total energy also at point A by conservation of energy, which is 147 joules. Calculate the PE and KE at point B. At point B, the height is 0, so mgh equals 5 times 9.8 times 0 equals 0 joule. Since the total energy at point B equals potential energy at point B and kinetic energy at point B, which is 147 plus 0 is 147. So, 147, which is the total energy at point B, equals the potential energy at point B, which is 0, plus the kinetic energy at point B. So, solving for the kinetic energy at point B, this is just equal to 147 joules. Find the speed of the ball at point B. Using the formula V equals square root of 2 times Ke over m, we have 2 times 147 divided by 5 is equal to 7.67 meters per second. Find the PE and KE at point C. At point C, it is at a maximum height of 3 meters. Therefore, m times g times h equals 5 times 9.8 times 3 is 147 joules. And since it stops momentarily at point C, the velocity is 0. Therefore, kinetic energy at point C is 1 half mv squared, which is 1 half 5 times 0 or 0 joule. Hence, the total energy at point C is 147 plus 0 equals 147 joules. If there are no more questions, then let the students complete the classwork until the end of the period. Have a nice day.